Hi students, welcome to my lectures on non-ideal reactor design. In the first two sheets, I am going to discuss about a brief about last class. And I request you all to follow my lectures from the beginning because every lecture is connected. So this is what the brief, that the reactors which behaves non-ideally, which could be CSTR, PFR or packed bed reactor or any reactor. To find out the conversion in a non-ideal reactor, we need three informations. One is kinetics, second is residence time, that means how molecules spend inside the reactor, and third, mixing models, how every molecule is mixing with the other molecules. So if you know all the three informations with you, we can able to predict the conversion. And in the first few lectures, we are going to discuss about getting the time information using RTD experiments. Objective is to get the residence time distributions and few other parameters which describes the non-ideality in the reactor. So let us concentrate on the getting RTD informations. So this talks about what we get from RTD. RTD gives the information about characterization and diagnostics of non-ideal reactors. That means what is the non-ideality present and how much is the non-ideality we can able to get from observing the characteristics of the non-ideal reactors. And to observe the characteristics of the non-ideal reactors, we observe in terms of few parameters. Those parameters of E of t, residence time distribution, cumulative time distribution, mean residence time, variance, skewness, mixing models. So these are the some characteristics we can get from the RTD experiments. So that is why in the first part we are going to discuss about characteristics of the reactors through RTD experiments using these particular parameters. So the first part describes that let us with few examples, let us get the information about all the characteristics, that how we can able to calculate, and second, apply these characteristics to the ideal reactors, because first of all, let us see how these characteristics looks for the ideal reactors, so that you can have a reference point. Using that particular reference point, we can compare the non-ideal reactors. In the part 2, we are going to discuss about the mixing models, which comes later part of the story. Don't worry. Right now, let us get the information, that is characterization of non-ideal reactors using RTD experiments. So once let us start and RTD experiments. What is called residence time distributions. That means information about the molecules spending in the reactor, especially the time information. Okay. You can observe, I represent the non-ideal reactor with a circle where some reactants are going inside and some product is coming outside. The blue circles represent the regular reactants which are going in and product that is coming out. So you can see the red circles. Red circles are my tracer. Tracer, that means the tracer is a substance which can able to we can able to detect at the outlet. So these tracer molecules will travel the path along with the regular molecules. So we can able to detect the tracer at the outlet, so that we can get the information about how the other molecules spend in the reactor. That means there is a regular reactants going in and product is coming out. In between, we are going to inject some amount of tracer which can be detected. Tracer which will not be get reacted in the reactor. It is just follow the path of the molecules. So at the outlet, we are going to take out the sample at different time intervals. So we can able to get information that how much molecules are coming at the beginning of the time, how much molecules are coming at the end of the time, so that you get some information about the time spent by the molecules in the reactor. That means if you can able to find out the tracer, that means the same path will be followed by the other reactant molecules. That means measuring the time of the tracer, that means indirectly measuring the time of the reactants or product molecules spending in the reactor. So the process of finding and plotting the information about the tracer along with the time is called resident time distribution curve. It is first proposed by Macmillan and Weber. Okay, and later this particular tracer experiment is organized by Professor P.V. Danckwerts in the year 1950. So what we get this information about the time spent by the molecules in the reactor through the curve which is called E of t curve. That means by plotting the E of t curve, you can get the information about the time of the molecules. Tracer curve is performed to get the information about residence time distribution. Okay, the blue one is a reacting molecule, the red one is a tracer molecule. And what should be the properties of the tracer that you are putting in the non-ideal reactor? The tracer properties can be, it should be non-reactive. That means if the tracer molecule will consume in the reactor, you cannot detect at the exit. The first tracer property should be non-reactive. It can be easily detectable through titrations or other measurement techniques. You can able to find out the amount of tracer at the exit. Completely soluble. Okay, it should be, that means it has to be soluble in the reactants, through the reactants, because if it is not soluble, it won't follow the path followed by the remaining molecules, reactant molecules. So that if the tracer should be dissolved with the other molecules in this mixture, so that the path followed by the reaction mixture is the same path followed by the tracer molecules. It should be completely soluble. Physical properties, that means densities, viscosities, so it should be similar to that of a reactant molecules, and it should not adsorb to the walls, so that it should not, if tracer molecules gets adsorbed on the walls, you cannot detect at the outlet. That means few tracer will get remained in the reactor for a remaining period of the time, so you cannot detect. So that means it should not be stick to the walls. So there are other important properties. We can read the textbook. So main important properties are listed out here. So tracer, okay, it can be colored and radioactive material, so that you can colorimeter whatever the meters which can able to detect the color. Okay, so that tracer should be colored and radioactive material. If it is a radioactive material, it can be simply detected by exit through the radioactive detector. Okay, and inert gas, if it is a gas phase reaction, you can send some amount of helium or nitrogen into the reactor, so that it can be easily, it won't get consumed. Example, such a reaction is happening, so nitrogen kind of materials or helium kind of materials cannot be reacted in the reactor, so which can be detected at the exit. So easily detectable, acid or base. Normally we perform this experiment using acid and base. We inject certain amount of tracer, in the like this acid, we inject into this particular inlet chamber, and we detect at the exit. So we take out the sample at different intervals of the time. You can titrate against a base, so we can able to get that with at what time what concentrations of molecules are coming out of the reactor. So there are number of injection methods. The popular injection method is a pulse input and step input. What is the pulse input? Pulse input means along with the regular reactants which is flowing in the reactor, and all of a sudden you inject certain amount of molecules at time t equal to 0, and at the exit you are going to measure how much amount of molecules are coming out with respect to time. So this is called pulse input. The second input method is a step input. The step input means along with the regular reactants, continuously you are going to pump the tracer, so that you can detect at the exit. Here only a few amount is injected at a time. Here injection is continuously along with the reactants. The tracer molecules are injected with a certain flow rate. So most simplest of this is a pulse, so that you can, with less amount, you can able to get the information of the time of the reactants. Here more amount of tracer, because from the beginning of the experiment till end of the experiment you have to continuously pump the tracer in the reactor. So here the cost, it is not cost effective. So in this lecture series we are going to discuss about the pulse input. Simple, certain amount of tracer molecules are injected at time t equal to 0. Okay, so based on this injection, and you are going to detect at the exit how many molecules of tracer are coming out at what point of time, so you can able to make this residence time distribution curve. So this is how a residence time distribution with pulse tracer input experiment. So at the injection point, because if the reactants are flowing at a flow rate of nu, which is some liter per minute, with this kind of reactant flow rate into the reactor, at certain point of time, certain amount of tracer is injected. N0, total number of moles, I mean N0 is the initial number of mole injected into the inlet point. So what happens? A tracer molecules goes inside, mixes with the regular reactants, and will come out at the exit. At this exit point, you are going to take out the sample at different intervals of time. So what happens? I mean, the tracer curve looks, I mean, in majority of the cases, you may look like the tracer curve experiment. That means at time t equal to 0, no concentration of molecules at the exit. At time t equal to t, certain concentration of molecules are coming out. So more is the time, the concentration of the tracer will be increasing, and after certain point of time, the tracer molecules are, I mean, start getting depleted inside, because and the concentration of tracer molecules will come down. So this is all the typical curves looks like. There are number of other curve natures are there. So let us discuss about as simple as possible. If you put a tracer inside the reactor, and this is how the residence time distribution curve looks like. The concentration will initially rise and then drop. Okay, because this is the inlet. This is the inlet curve. That means at time t equal to 0, certain amount is suddenly injected. This is exit curve. This is how the concentration will increase and decrease. And to get the information about residence time distribution, let us divide this into number of blocks. You can see I have divided this entire curve into a number of rectangles. So smaller is the rectangle, more is the accuracy. So at a certain time, at t and t plus delta t, certain concentration of molecule comes out at the exit. Okay. So let us take some balance of this particular intermediate time. So amount of tracer material leaving the reactor between the time t and t plus delta t is nothing but delta n. Delta n is the moles of tracer that comes out at the point t and t plus delta t, which is represented by delta t. Delta t has the unit of mole. So which is nothing but C of t into nu into delta t. What is C of t? What is the concentration during this t and t plus delta t, which is C of t, into nu, which is a volumetric flow rate that is coming into the reactor, into what is, at what time difference you are trying to measure the moles between t and t plus delta t. So moles of tracer coming out of the reactor between the time t and t plus delta t is nothing but C of t nu into dt. For a clarity, I have represented the unit system. Concentration is measured in terms of mole per liter, volumetric flow rate is measured in terms of liter per minute, and delta t is measured in terms of minute. If you can see, liter cancels out, minute cancels out, and delta n, that is moles, is nothing, delta n is nothing but moles. What is N0? N0 here is representing at time t equal to 0, how many total number of moles of tracer is injected. That is called N0, is the total moles injected at the injection point. And what is delta n? It is nothing but moles that has came out at a time t and t plus delta t. When you divide delta n by N0, that means smaller moles are divided by total moles. It's nothing but fraction. Delta n by n. That means the moles that comes out of the reactor at t and t plus delta t divided by total moles that is injected will get a fraction of moles that comes out at this particular point between the time t and t plus delta t. So which is nothing but delta n by n0 is nothing but nu into CTR, that is concentration of the tracer. Remember, don't get confused with the CT. Concentration. We are not talking about the concentration of reactants here. We are talking about the concentration of the tracer. That is why it is a concentration of the tracer which you are measuring at the exit is represented by CTR. So majority of the confusion happens. So I have cleared the confusion now. Okay. Or how to get the fraction of moles that comes at the time per t plus delta t, which is nothing but delta n by n0, nu into CTR of t into delta t by n0. This delta n by n0 is nothing but fraction of molecules leaving the reactor between the time t and t plus delta t. Let nu into CTR into n0 is represented by ET, which is called residence time. Okay, E of t, residence time curve. Finally, you have to get this E of t curve. And what by delta n by n0 will become? Delta n by n0 will become E of t into d delta t. So you can see fraction of molecules information you can able to get, that is coming between the time t and t plus delta t, you can able to get through the information E of t and delta t. E of t into delta t, it gives the information about the fraction of molecules leaving the reactor between the time t and t plus delta t. Then what is the unit of E of t? Because fraction unit should be unitless, so that time delta t is the minute, E of t should be 1 by minute. That means the unit of E of t will be 1 by minute into minute will give a unitless number, which is the fraction. Okay, let us move ahead. So what is delta n? CTR into nu into delta t. It's in differential form. Okay, if you keep the things in the differential form, you get delta n is equal to concentration of the tracer at time t equal to t into volumetric flow rate into delta t. In a differential form, it will become dn, which is concentration of tracer at time t equal to t into nu into dt. Finally, if you integrate this particular equation from time t equal to 0 to t equal to infinite. Why it is infinite? If a tracer you are getting at till infinite time, you are getting some tracer at the exit, this graph will extend. It won't get to extend to infinite, but let us, for the sake of easiness in the integration, let us integrate this n0, I mean this dn up to 0 to infinite, which is nothing but, if you apply integration to the both sides, integral dn is equal to integral nu into CTR into dt. Integral 0 to infinite dn is nothing but n. That means if you integrate the total moles that comes from 0 time to infinite time is nothing but n0. On the left hand side of the integration, you get n0. N0 means total moles that is in the, because total moles that comes out of the reactor till infinite time will be equal to initial number of moles that is injected. So initial moles that is injected in this particular on the left hand side is n0. So finally n0 is 0 to infinite nu into CTR into dt. So total mole that comes out of the reactor from time t equal to 0 to t equal to infinite, that is, this is particular number. So how to get E of t information? Finally, we have to get the graph of E of t versus time, because from the E of t versus t graph, you can able to identify what particular fraction of molecules spending how much amount of time. Slowly we go from C of t to t graph to E of t graph. To plot E of t graph, you should know information about nu CTR by n0. Okay. How to get n0? N0 you can get from the integration 0 to infinite nu into CTR into dt. If you substitute n in place of n0, if you substitute this particular integration, then you can get E of t graph using this particular equation, nu into CTR of the concentration of the time tracer divided by 0 to infinite nu into C of t into dt. Volumetric flow rate is not changing. If you assume that both nu and nu get cancels out, finally you can get the E of t graph if you know the concentration of tracer at a particular time divided by integral 0 to infinite C of t dt. What is integral 0 to infinite C of t dt? Is nothing but area under this particular curve. As you know, integration is nothing but area under the curve. Okay. So you can get information that E of t is nothing but CTR by integral 0 to infinite C of t dt is nothing but concentration of the tracer at the specific time divided by area under the curve. Using above 6, let us draw you get the from C of t versus t time, let us get the E of t versus time using a small problem. Before I attempt the small problem, I am going to use some integration formulas which are very simple. Okay, remember these formulas. If you have the 2 points, if you have the 3 points, x0 and x1, 2-point formula, 0, 1, 2, 3-point formula, 4-point formula, 5-point formula, 6-point formula. So I am going to apply this particular trapezoidal rule, Simpson's 3/8 rule, quadrature rule, general formula, So I'm going to apply any one of this depending upon the situation. I'm going to use this particular formulas. You can keep this in picture. Let us proceed with the problem. With given pulse tracer data, find the residence time distribution data and analyze. That means I have to plot E of t graph, residence time distribution graph. The tracer curve data, that means some people have injected some amount of tracer in the, let us suppose it's a non-ideal reactor. At the exit, they have measured the concentrations. At time t equal to 0, nothing of the tracer molecule is coming. At time t equal to 1 minute, 2 gram per liter has come. 2 minutes, 6 gram per liter. At 3 minute, 4 minute, 1. At 5 minute, nothing comes. That means if you plot this, you get this particular curve, right? So let us to get this E of t information, I need to know area under the curve first. That means area under the curve, integral 0 to infinite C of t dt. In place of infinite, now last time is 5 minutes. Okay, so in place of infinite, you have to put 5. That is the last value of concentration you have got. So integral 0 to infinite concentration of tracer into dt, that means this is a constant tracer, that is integral 0 to 5 CTR into time. I am going to apply, first of all I need to get the area under the C curve, that means this infinite curve, infinite, I mean to say that this integration value. So I have the data, I am going to apply this particular integration 6-point formula. I have total 6 points, 1, 2, 3, 4, 5, 6 points. I am going to apply the 6-point formula. From the 6-point formula, I have to, in place of is x0 to x5, f of x dx. In place of f of x, now I got the concentration. The values of concentrations are given here. So I replace this f of x with C, concentration of the tracer data. I get some value, which value is nothing but the area under the curve. Okay, this is a 0 to 5 concentration of tracer into dt is equal to 3 by 8 into h. Concentration time t equal to 0 plus 3 times concentration of time equal to 1 plus 3 times concentration of time equal to 2. So you apply the formula, and what is the h? 5 minus 0 by 5. Okay, that is the step length. Okay, 5 minus 0 by 5. So I know all the data. Simply I substitute the concentration data and step length data. Finally, I get integral 0 to 5 CTRT dt is nothing but 13.125 gram per liter, okay, into minute. What is the unit of this particular integration? Concentration has the unit of gram per liter, dt has the unit of minute. That means the area under the curve, that means the denominator one, the area under the curve, that means the area under the entire curve we have evaluated using integration formulas. So area under the curve you have got around 13.125 gram per liter. Now simply I use the formula E of t is nothing but C of t by integral 0 to 5 CTRT dt. Let us plot. I know the t versus concentration data. Now I have to plot t versus E of t data. E of t data is nothing but CTR divided by area. Area I have got 13.125. That means every value of the concentration I have divided with this particular total 13 point. Example, 0 by 13.125, 2 by 13.125, 6 by 13.125. If you evaluate, you get a E of t graph. Now simply you have to plot time versus E of t. So what is the C of t graph? So if you plot t versus concentration, it's called the C curve. If you plot t versus E, it's called the RTD curve. So this is how the RTD curve looks like with the given data. Okay, now from the RTD curve, what information we have got? If I divide the curves into number of segments, the first segment is A1, second segment is A2, A3, A4 and A5. I divided this particular E of t graph into 5 segments. I mean for clarity, okay, don't worry. What information it is giving? What is the area under this particular curve? E of t is area under the curve up to 0 to time t equal to 0 to 1 is A1. The area under the curve between time 1 to 2 is A2. The area under the curve between the time 2 to 3 is A3. Similarly, 3 to 4 is A4 and 4 to 5 is A5. What A1 indicates? A1 indicates out of the tracer molecules, the A1 is the fraction of tracer molecules that is exiting between the time 0 and t1. That means, example, if I pump certain amount of molecules, out of the certain amount of molecules at the inlet, at the exit, A1, that means among the injected molecules, the fraction of molecules which is A1, that is exiting the reactor between 0 and 1. A2 is the fraction of molecules that is exiting the reactor between 1 and 2 minutes. A3 is a certain fraction of molecules that is exiting between 2 and 3 minutes. Like that, the information about the time of molecules spent in the reactor, we can able to get the information. This is what the beauty of residence time distribution curve. Okay, let us move ahead and find out how to get the values of A1, A2, A3, A4. Directly, if you can able to measure the area from the graph, you can get the information. The alternative way is use the integration method. That means if you want to get the A1, apply the integration 2-point formula and 0 and 1. If you want to get the information about the area under the curve between 1 and 2, which is A2, apply the integration between these two values. So like that, to get the values of A1, A2, A3, A4, A5 through the integration methods, apply individually between the points 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5. You get the all areas informations. So that's what I have done. Let us find out the areas. How to get the formula? How to get the, let us get 2 point. Let us time t equal to 0 to 1, integral 0 to 1 e of t dz. Area under the curve between the time 0 and 1 from the graph, which is nothing but A1. You can get from information that you can use the 2-point trapezoidal rule, so which states that half times the first point and last point. First point is time t equal to 0, last point is time t equal to 1. So you get some information. I get fraction A1 information is 0.076. Similarly, I apply this 2-point formula between the different times, which is 1 and 2, 2 and 3, 3 and 4, 4 and 5. I get different informations. Area informations A1, A2, A3, A4, A5. So let us list out this summary that A1 is 0.076. That means 0.07 fraction of molecules comes between the time 0 and 1. 0.3 fraction of molecules exiting the reactor between the time 1 and 2. 38%. That means if you convert this, the 7% of molecules comes at 0, 1 minute. 30% molecules comes at 1 to 2 minutes. 38% molecules comes between 2 and 3 minutes. 19% of the molecules comes between 3 and 4 minutes. 3% of molecules comes between 4 and 5 minutes. If you summate everything, you get the fraction of molecules. That means if you summate everything, the fraction should be close to 1, because I have applied integration formulas. There will be a least accuracy because my time step length is more. If you can able to reduce the step length and apply the integration formulas, you get the more accurate one. So finally, the agenda is all the fractions, cumulative of all the fractions should be equal to 1. So we have got close to 0.989, which is sufficiently fine. So this is what the beauty. Okay, now I have got the time informations, because to design the reactor, I need to find out the time information first. Now I got the time information, how much time, how much fraction of molecules pending in the reactor. Okay, let us move for the next class to get the more information about f of t, which is cumulative distribution curve. Okay, let us see.